Today, we'll talk about a recent gamma-ray burst, creating biofuel from waste, and check out how these soft robots grow like plants. This is NSF Science Now. Recently, a massive star was detected running out of fuel and collapsing in on itself, transforming from a star into a brand new black hole right in front of our eyes in mere seconds. Two teams of NSF-supported researchers obtained a deep, detailed image of the afterglow of this historic explosion utilizing the same optical infrared telescope.
We used the Gemini South Observatory in Chile, an NSF-funded telescope, to observe the afterglow of GRB 221009A. So the afterglow is this emission that arises after the initial burst of energy.
This gamma-ray burst took place a mere 2.4 billion light-years away and is the brightest ever observed.
So this gamma-ray burst, GRB 221009A, is the brightest of all time. A normal gamma-ray burst is a light bulb in brightness. This gamma-ray burst is like turning all of the floodlights on in a stadium.
While not visible to the human eye, the collapse was caught by satellites high above the Earth scanning the sky.
The burst would have gone off in the high energies and the gamma rays, and that burst would have lasted mere seconds. The orbiting robotic satellite telescope would have detected that. It would have slewed very rapidly to the location on the sky to determine the precise location, and then it would have sent out an alert to astronomers worldwide so that they could follow up with observatories on the ground and elsewhere to be able to observe this event.
A long afterglow observable by ground-based telescopes followed the explosion caused by the collapse of a massive star. This once-in-a-lifetime event will allow astronomers to understand gamma-ray bursts better. Both NSF teams are excited to learn all they can.
This is the only chance in our lifetime to study this type of explosion at such a nearby distance in exquisite detail and actually be able to follow it across the electromagnetic spectrum for a very long time to come.
This opens up new questions and new avenues for exploration. As an astronomer, this is a reminder that the universe is never fully figured out, and there's so many more questions that we can explore and avenues for research.
In the U.S., over 1.3 billion tons of waste are created every year. What if this waste could be transformed into something useful? An interdisciplinary team of researchers at Worcester Polytechnic Institute is looking at ways to use food waste to make a renewable and more affordable fuel alternative to oil-based diesel.
So in our lab, we have created a new process which uses temperature and a catalyst to convert food waste that we make every day into a precursor that can be converted into renewable diesel fuel.
Currently, rotting rubbish in landfills generates high levels of methane gas and CO2, greenhouse gases, which contribute to global warming.
If we can divert that from landfills to a usable fuel, then we're working to solve two problems at once.
The team has created a process that could bring gas prices as low as $1.10 per gallon and has a variety of possible uses.
This process can be used for an array of waste products from sewage sludge to wood waste, and can also be used in various supercritical processes to make an array of fuel types, from gasoline to power our cars all the way to jet fuel to power our planes.
With the method in place, the team will focus on making it easier to scale and bring it to the commercial market.
National Science Foundation has invested in the long term in instrumentation that allow us to understand that mixture in ways that allow us to optimize the process and bring it to commercial reality much more quickly than we'd ever be able to do without those resources, in order to bring this technology to the public in the next 3 to 5 years.
Engineers borrow from nature to create the first ever plant-inspired soft robots that grow like plants.
Plants and fungi are great examples of natural organisms that use growth as a way to explore and navigate their environments. We were really inspired by this work and wanted a soft robot that could do the same.
Current soft-growing robots drag a solid tail of material behind them, making it difficult for them to navigate tight spaces. But plants don't have this problem. Plants grow by using water to transport the building blocks that become solid roots as the plant grows outward. NSF-supported researchers at the University of Minnesota Twin Cities mimicked this process by developing a soft robot that uses light to transform liquid into solid material.
So we took this idea from nature and then we translate it into an engineering system in which the soft robot turns liquid monomer into solid polymer or plastic at the end of its body.
Possible applications are endless.
We're really excited about these growing soft robots to be used in a variety of different applications, which can include burrowing underground, deploying infrastructure, or navigating and exploring hard-to-reach areas.
These soft-growing bots could even one day be used to save lives.
Right now, there's a few catheter robots that have a lot of promise, but this really opens up a whole new world of possibility with directions we can take. Easily in catheter robots. These are long structures that if they could just grow instead of being dragged, they could solve a lot of problems that catheters face and actually prevent them from helping treat patients. Getting catheters so small that they could actually grow delicately through tissue and find a cancerous tumor without injuring other cells. And we can do that without causing the trauma that some modern surgeries sort of have to cause at this time.
This research would not have been possible without outside collaboration.
So from the very beginning, this project was all about collaborating with people from very different backgrounds, because we knew we needed solutions that our own field couldn't provide. And that's when the material scientists gave us a lens we could look through. And through that lens, we saw nature in a different way and saw that nature can already do this. Plants and fungi can do this, and it turns out the material scientists can also do this.
For more research news, visit our channel. This is NSF Science Now. I'm Dina Headley.